Okay, I think we should making those jokes. So anyway, um, I'm going to finish the discussion on the graph neural network here. Now notice that there's another class at Stanford that spent a whole quarter to talk about graph neural network. So here we are not trying to compete with the other course to talk about the details, but I would like to take a more global view to show you the relationships between the graph neural network and the learning of a graph and the learning of metaphor. So you can kind of see the big picture. And hopefully by now, you will notice one major similarity is that in all of the, regardless of whether we deal with the graph or we deal with the metaphor, that always include one step, and that is that we either map the metaphor element on the metaphor onto a vector space, or we actually put a nodes on the graph on a vector space. Okay, so this upstream task is sort of universal. We have some data that are entangled or very complicated, or they can be expressed either as a graph or as a metaphor, but you're not dealing with it directly. You try to actually find out what is the right way to represent it in the simplest way, and that part is universal. Now the details, which is actually the devil part, is actually very different because obviously graph and metaphor have different property, but those properties are the thing that change, okay? So you see what I mean? So the grand strategy is actually the same for both graph and metaphor, but the tactic that actually enable that mapping is different. Okay, so by actually connecting the two in one course, it kind of compress the time, but it give you, hopefully it can give you a better overview about the strategy, okay, in the strategy level, how we deal with things, and then from that you can learn what is the right tactic for a given set of data. Okay, so here in the last lecture, we spent the whole lecture basically to talk about two items, how to embedding the nodes of a graph in the vector space. Okay, so this is actually the task. Now here we want to extend that task, okay? In this lecture, I want to say, I want to deal with a set of graph. For example, a set of microstructure, pole network, a set of DEM simulations, a set of proteins, molecule, a set of whatever. So a collection of them, and I actually want to put each of the corrections into a position vector in the vector space, okay? So you see the difference? So the two work are obviously different, but they are actually related. So I will recap a little bit about the node embedding. Forgive me if I actually repeating myself multiple times, and then I will talk about the graph. And as you can see, the major bottleneck, let me rephrasing this. In order to able to embedding the graph into the vector space correctly, there are two necessary conditions at least. The first one is that you have to embedding the nodes successfully into a vector space in the spatial approach. And the second one is that you have to actually successfully pooling those information to put the entire feature vector space of the nodes into one feature vector for the entire graph, okay? So in general, you can actually argue that this is actually a type of compactions. So let me use the right pen. So the graph embedding is actually some type of data compactions, but is actually compacting the topological informations and the feature of the individual nodes into a vector space. And this is actually compactions that are actually more spatial or topological driven. We try to put all the latent space information that are actually stored in nodes, convert it into a graph. So I will actually talk about the difference and the similarity. Okay, but what I try to convey to you is that even though the details are actually different, data point can be actually viewed as nodes in a graph if you can actually find the edge relationships, or they could be in the metaphor. In most cases, they are simultaneously, both two interpretations are actually acceptable. Okay, so I'm just trying to put some dialogue to converge us into the metaphor learning to finish the graph. Okay, so in general, in practice, most common case is that you have a point cloud. I think this the geometric learning, one of the starting point is related to the video game where they want to map Michael Jordan's face onto a three-dimensional object and they want to actually have a facial expressions, okay? So one way you can do it is that you put the point of you do a motion capture by putting a point cloud. Initially it's 2D of a human face with some dot, and then you measure the Euclidean distance of different nodes, okay? So from that, you can actually learn a few people, how does, if I smile, how does this point clouds move, and then you can find the eigens, you can find the underlying pattern of how to map, how to create the deformations of the point set that convert a face with no expression into a smile. Okay, so that's the underlying idea. So in this particular case, the actual point are actually both in the manifold and also in the graph, because you actually view it in the graph because drawing the triangle on the point set is actually easier than actually getting the curvature of the entire face, right? You see what I mean? But what you actually typically did is that you're first analyzing it on the graph, and then you project that update nodes onto a metaphor to recreate a 3D face, okay? Your face is not a graph, obviously, okay? You can mesh it into a 5-element mesh that kind of give you the sense of the metaphor, but your face is actually better represented as a metaphor, okay? And then now we show this figure many times. In the last lecture, we are dealing with only this part. Okay, how do we do the convolutional neural network? And here I want to actually start talking about the isomorphisms and also this part of the graph. Okay, so as you can see, I actually have initially I have a graph that are actually already reduced representations of the three-dimensional or whatever information that I have that are actually reduced by actually creating a discrete relationships instead of a continuous. Now, I actually what I actually need to do is that after we obtain the node embedding, I will try to actually conduct the graph. I actually collapse those information into a single graph representations. I haven't talked about the decoder, but the building the encoder is necessary to actually ensure that we can build the decoder. Okay, so we talked about that last time. Maybe I should not talk. Okay, so after the pooling, you also typically using you add the field multi-layer perceptron. Okay, the reason to doing that is actually not for any particular reason, but to add the nonlinearity flexibility to it so that it can actually rearranging or actually create another nonlinear mapping to make the feature more regularized, meaning that to arrange the distance a little bit so that the graph that are actually closer to each other actually remain closer, okay? So I mean, so in the graph pooling, what we care is just to make them distinguishable. And then we want to make sure that we don't mess with the order. If I have a 3 different graph and then graph A should be closer to graph B, if I actually have 3 graphs and then graph A is the graph 1, graph 2, graph 3, and then graph 1 is actually very close to graph 2, but graph 1 is very far apart to graph 3, I don't want to mess with the order of their closeness, okay? But I actually don't care about, I don't necessarily really measure the distance and preserve the distance in the graph embedding. If I cannot do it perfectly, I can still have the multi-layer perceptron to add the nonlinearity to further deform my lattice vector space. Much about the details, but if we remember that, in the spectral approach of the graph, we actually view the graph globally. We try to obtain the eigen decompositions of the graph Laplacian, and from that we establish a representation. So everything is global. The problem is that it's really hard to do graph embedding if you have different number of nodes. Okay, so how close is a 2x2 matrix that have a component 1, 2, 3, 4 versus a 3x3 matrix have 1, 2, 3, 4, 5, 6, 7, 8, 9, as a component is really hard. It's ambiguous questions. So instead, the spatial approach or the message passing approach is taking the is actually getting momentum because it doesn't have that kind of limitations that you don't actually need to have a fixed number of nodes. Okay, so the previous one, we can deal with different number of edge, but the nodes has to be fixed. And then that would actually, okay, so related to creating a conditional graph, actually what we talked about before. So the node embedding task, as we talked about last time, is to converge a particular graph, usually a ray graph, onto the vector space that gives you the right positions, right? And we actually talked about these two in the last lecture. And I think that we go over that a little bit. Let me recap it. So the key here is that if we actually have a grid system, if I actually make a point, and then if we look at the neighborhood and we want to aggregate some informations, all the nodes have the same number of neighbor. So you can consider a convolutional neural network as a special case of a graph neural network where the computational graph are actually fixed. In this case, for node A, you have this neighborhood, the two hope neighborhood. In node B, you have this neighborhood. In C, you have this neighborhood. In D, you have this neighborhood. So let's say I want to predict the influence of the nodes among each other. I can do it in the embedding, but I actually need to deal with the different topology, which doesn't occur in graph convolutional neural network. In the spatial Euclidean space convolutional network. I think I would actually skip the details, but last time we talked about the aggregations, which is actually also what relevant here. In general, what we actually want to do the embedding is to create a consistency vector space so that if I aggregate these informations and then using a neural network, I can actually create a consistent predictions or representations that are actually node B. Okay, I skip the details, but long story short, we can actually consider the neural network setting as training these functions. Okay, given adjacency matrix and a hidden variable, this is actually where we create the aggregation of one embedding. We actually try to create functions that actually allow us to do to actually create a vector space. And this is actually the mapping that are actually coming from the adjacency matrix and the feature of the entire space onto a vector. We also talk about the graph attentions. This is actually very similar to the previous network, except that I would actually add the attentions mechanism that we are going to train it by co-training the edge attentions AIJ. AIJ actually the attentions are on the edge. So you can see the AIH actually exists on the edge, and that it actually indicates the importance of the influence of a given nodes set J on the target nodes. Okay, so this is all good. Then we also talk about the permutations important. If we're reordering it, the label, you should actually either get the same results, which is we call it invariance, meaning that if I add those nodes 1, 2, 3, 4, 5 as a one label, and then I have another graph that are all identical except that I label it as a 2, 3, 5, 2, 1 for 2, 3, 5, 2, 3, 5, 4, 1. Okay, so now the number is different. I should actually get the same mapping independent of my label. If it's actually that is the case, this is a permutation invariance, and in many cases, we will need that in particular if the ordering is actually have no physical meaning and arbitrary. Okay. On the other hand, and that actually requires us to actually consider the aggregation operator that are commute. In the previous one, I actually applied the permutation tensor on the adjacency matrix and the permutations tensor on the feature. X is a feature. I should get the same results. Okay. And another type is that when the order does actually make a difference in the feature in the adjacency matrix. For example, if this crystal is not order in random number, but they actually grow in this order, I'm just making something up. Okay, in this 1, 2, 3, 4, 5 order, and if you change the order, your prediction should change, then we need to actually consider to enforcing the permutation equivariance. In this case, I would actually, if I actually swap any order of this graph, I should actually able to get the feature that I also swap accordingly. You know the difference between the two? Let's go back. Here I do the same, but instead of getting the same result, the result is changing according to the permutation matrix. Okay, so well, depends on the problem. You need to actually consider whether you actually fulfill this criteria. Now, this is actually what we happened in the last lecture. And then the last lecture is basically on this. Okay, so I have a graph, and that graph have a adjacency matrix. Adjacency matrix is how these nodes are actually connect to each other. I think okay, let me ask the questions. By now, does everyone know what is adjacency matrix? Okay, so that's good. And then X is actually the feature, is actually a rectangular matrix that have the row equals to the number of nodes, and the column number of column equals to the number of feature. Okay, feature is any attribute of the nodes. Okay, if the node is a human, it could be how tall you are, how heavy you are. Okay, or it depends on what you want to predict. Okay, if you want to, nodes could any attribute of the nodes. It could, for a crystal, it could be the size or shape, orientations, etc., etc. Okay, now, but this is actually on the graph. So the node embedding is basically to convert this known feature into a hidden feature, but actually taking out the graph connectivity. We still have basically to create an edge. So the node embedding is actually to convert this information into edge. Edge is actually the Latin space, is actually the Latin vector for a graph, for nodes in a given graph, for a given graph. Okay, so the last lecture, what we talk about is just do the edge. Now, in order to do the graph pooling, we are focused on that boot circle. This is what we are going to talk about today, and it's actually pretty simple compared to the node embedding. I'm just going to show some options, but in order to do that, the graph embedding requires us to have both H and A now as an input to create another new, let me use the same notation, ZG, and that is actually the representations of graph, of the entire graph, okay? Now, this is actually one vector, okay? You see what I mean, okay? So how do we do it? A very simple way. We talk about it, and in some literature, you can also see that you sometimes call it filter, because you do actually using the opportunity to filter outcome informations and collapse all the information into one vector. Okay, so one simple way is actually very easily understandable. You can actually do something like this. This is actually a global mean, max, or sum pooling. Okay, what it means is that if I have a graph, let's say that, and then I already have a hidden layer, hidden lattice vector, for example, 1, 2, and 2, 5, okay? What I actually, so this is actually a graph. what I actually going to do is that I simply put this thing, I just take the mean, max, or sum together to form a graph. So the entire, to represent this entire graph, if I actually using the sum operator, I simply would get 3 and 7. Okay, so this is actually very simple. And then I would actually have the dimensions in this particular case of the Latin space vector would be identical to the dimensions of the Latin vector for the individual nodes. Okay, you see what I mean? I'll simply just, or I can take the average, and you can immediately see that you can actually, it's actually, that embedding is not limited by the size of the graph, because I can give you another example, 1, 2, 1, 0, and 0, 1. Okay, if I actually, this time, if I use the max layer, a max operator, I will simply get 1 and 2. Okay, so I will actually get a vector space. Now, then the problem is the following. I basically have no control of my control of the entire embedding from the individual nodes to the graph are only through those operators. And they are actually quite limited, right? As you can see. Okay, I would actually, in this step in particular, if my graph is like, in this case, if I actually want to build a decoder, I need to use this as an input and then allow me to map it back into something like this, right? Okay, you can see in that the decoder, so the Latin space information itself is not enough to actually reconstruct the entire graph, but I would actually need to build it in an auto-encoder manner to actually inject the bias again, inductive bias again in the decoder in order to get back the initial graph. Okay, and depends on what. So this mean, max, and then the sum actually become the operator for the data compactance. Okay, and you can actually see that in many cases it doesn't work. Okay, so and then there are new improvements to actually go over from that global pooling. And global pooling is actually also an active research area. How do I actually reduce the vectors space of the individual nodes into one global vector? Okay, maybe change the dimensions, maybe do something different, but what are actually the option we have is actually also active research. Okay. Okay, so far so good. This is supposed to be very simple. Okay. Okay, so let me just give this example, and then I will explain why I actually using this graph. The strategy we talk about actually looks like it's very simple, but sometimes simple thing doesn't work. And let me just go over some example, okay? Imagine that I simply have the lattice vector. Now the lattice vector is not the weight of the original vector. It's actually, we're already processing it from the node embedding, okay? So, and then I have these two graphs, okay? I just design that way for some purpose for demonstrations. As if you can see the pattern, how many of you already see the pattern? I write the graph A for one first, and then I write the graph 2, and then I try to have certain property. Can you see what is the property? It's like an SAT question, so I think just looking at that pattern, do you know how I come up with this pattern from this pattern? It's kind of scared. I feel like, did I calculate? Get the arithmetic wrong, right? Okay, look at this, and then this, I just add 10, right? Okay, so looking at this, actually start to doubt myself. And then this, I just minus it by 10, right? Okay, so I have 4 elements, add by 10. I have 4 elements, minus by 10, okay? So now this is pretty obvious what would happen. If I actually apply the sum operator to condense the entire graph into a Latin space, okay, so these two graphs are actually obviously very different, okay, because the Latin way are actually different, so they represent a different structure or different way and different topology structure, I don't know. Now, this is actually not this is the Latin space, okay? This is belong to the Euclidean space. It's not the original graph. It's already in the Latin's thing. So this is actually Euclidean space of it with dimension 8. Now, if I actually did what I actually just told you to try to do the global embedding using a sum, I would get 36, okay? And if I actually take the average, I would get 4 in both. Okay, so now what I actually have the problem is that I have graph 1, okay, that looks like this. I have another graph that I actually look a little bit different, but then they all map into one vector. Okay, so you see what I mean? So I actually are losing the ability to distinguish graph 1 from graph 2 if I actually do the pooling. Now, actually, why do I actually care about their difference? Why do I actually need to care about the difference? Because I actually need them to preserve the difference so that I can actually using it for my downstream task, or I need to using it for decoder, right? If I actually just in autoencoder applications, if the two different graphs are collapsed into the same Latin vector, there's no way I can build a decoder that distinguishes them as a different graph again, right? Okay, so this is actually game over for this particular case. If I actually compress the data this way, I'm destined to make a wrong predictions, okay? Did you get this part? The max one will still work, okay? So obviously they have a different max. In this case, this will be 8 and 14, okay? So so that tells you that, so Sabina look a little bit surprised. Or you just, you're actually working on others, reply email or Ronnie, right? So, okay. Okay. It's okay, it happened to me many times. People look very intense, but they are looking at. No, I'm just kidding, sorry. Okay, so let's look at the other case, okay? Now, I am actually consider another case where I have a Latin space look like this, and I have a Latin space look like this, okay? Now, they are actually very different set of number, right? Now, this time, the max pooling would be terrible because these two different graphs that will be actually mapped into the same Latin vector, but the average and the sum are actually still create a representation that is distinguishable, okay? So now the question is that when you do the CAS project, if you don't do anything special, you have to pick either the sum or the average or the mean. So which one should you pick? Or you should try all of them and see what happens. And that is also the majority of the paper I'm reviewing. So there's a new network, and then there are 10 options, and then I just received 10 different options from 10 different, from the same author in different journal, and now reviewing the same problem. And sorry, I should recognize this part is record, but maybe it's better that it's record. But anyway, so this is not what we want, but so what we actually want is two things. If the graphs are somehow identical, and I need to clearly define what identical means, they need to map into the same vector. On the other hand, if they are different, they need to map into, they need to have different vectors, right? Okay, well, I can put in whatever I want, but I don't want them, if they are different, I can look at it, they're different molecule. I don't want to represent them with the same vector, because if that actually indicates it's not just a loss of information. If I lost information, I can use the inductive bias to actually recover that by minimizing the reconstruction error or the whatever. But if they collapsing into the same point, there's no way I can actually retrieve that information, okay? But once you lost the injective property, then the whole thing is actually bad, going downhill. Okay, so to address the same problem, if you probably remember I'm sure you will remember everything I said in the graph. So this is actually one example. Okay, these two graphs. Okay, so this is important to understand what is identical. Do they look quite close to each other? I don't think they look quite close to each other, at least to me. If you're actually a person that can immediately see the graph isomorphism, good luck. Really jealous of you, but I cannot. So, okay, in fact, they are actually isomorphisms, the graph that have isomorphism. And what it means is that they look identical, but if I actually look at the individual computational graph, if I actually put here, if I put a random nodes in this graph and then I look into the computational graph, I can actually find a pair such that they are actually identical. In particular, node A is corresponding to node 1 in these two graphs and 5 is to G. Okay, so if I actually pairing it in that particular way, then the combination graph are identical. Okay, you can try that. And then I think I take it from Wikipedia, which means that it's absolutely going to be correct. So I think, anyway, so, okay, so here I want to think about it in the context of the graph pooling, okay? If these two graphs in practice, they're identical, then I want them to actually map it into the same lattice vector space so that they are actually, so that I won't actually have a bifurcate subjective representation of them in the lattice space. Does that make sense? Okay, so how do I actually have it actually ensuring that? This has been the, and to be honest, in the original grid system, we really don't have that problem because in a grid, all your neighbors are actually identical. Okay, in particular, if you actually consider periodic domain, the combination graph are fixed anyway. Okay, but here I actually need to come up with the strategy so that I can actually get the same Latin vector of the entire graph if they whenever I actually observe isomorphism between the two graphs. So how do we do that? And I think that the typical trick is actually very simple. Like what we mentioned before, if I actually have a graph that actually doesn't look identical, I can actually sorting it. And then actually I can try to pair the, I can try to learn the coloring or actually learning the relationship between them and to check whether they are isomorphism. Okay, if they are, I can actually assign a particular order. Okay, and then I can actually recover, and then I can using that order to give us the indications of how close they are in the corresponding positions. In this case, the graph looks different, but if I look at the A, okay, the graph actually look very different, but then they're corresponding. If I actually following the coloring, I actually have the same computational graph, and so does the other sampling. So the common strategy, and this is actually coming from Yu-Xin Chen from Washington University at St. Louis, is that so the embedding on the node embedding is actually more or less the same, but I will actually add that sort pooling strategy. Instead of the naive pooling, I will add the coloring to it, and then I would actually using the coloring as the additional input to actually help me to actually help me performing the graph embedding. And also one common feature that, so this is one strategy, and then you can also add one deconvolutional neural network, and then before the dense layer. But typically in the graph pooling case, you do add the dense layer at the very end, just to add that nonlinearity. The same thing actually you would do in the, this is in analog to what you did in the node embedding. You aggregate the informations in the node embedding in the last lecture, but you put the neural network. This is actually just to give you more flexibility to express the latent space by adding a nonlinearity, so that you can change the way to actually adjusting it. Okay, another idea which I think is actually also very good is actually the, actually also again is from Stanford. So I think that is actually on the hierarchical differential pooling or depth pooling. The idea is actually very simple, and this is actually elucidated into the graph. I have a very big graph, okay? But then this big graph is actually can be clustering into, can be separated into multiple subgraphs. For example, this big graph, I can actually have 5 different subgraphs, right? 1, 2, 3, 4, 5. Okay, so for now, let's don't care about how they sum it up together. But if I actually collapse these 3 graphs into one node, I will get this. If I collect this 4 graph into this, I will get this. If I collect this 4 into this, I would actually get a pooled graph that are actually representing this, but with a simpler topology, right? Okay, and then I can actually do it again and again until I get one node. Then that one node will have not one feature vector, and then I can represent this entire graph with these representations by actually pooling. Now, this gives me more flexibility because by having different pooling, I can actually have different representations, okay? I just need to find a consistent way to actually group the nodes together to form a subgraph, and then I collect this entire subgraph with one node, with one feature, and I can do it multiple times. Okay, so this gives more flexibility. Typically, giving more flexibility is very dangerous because you need to control the flexibility. So this look like a magic. So now, but then let's about that way to do that. So let me show an example that doesn't work and show an example that work, and then I think that underlying reason that are very interesting. Okay, see how it did impact us. Okay, so again, I go back to the original 2 graph. Okay, and then I actually try to attempt a hierarchical pooling, and then I create a hierarchical relationships by something very simple. I simply just pairing all of them together, 2 by 2. Okay, so I hope I did not make an algebraic mistake here, which is actually, I think the other day I actually tried to correct my daughter's homework, and then I found that I actually make a mistake myself on the 3 plus 8, and then I feel very humble. But anyway, I don't know why, but maybe not enough sleep. But here, I hope that I don't repeat it again. So 1 plus 2 equal to 3, and 3 plus 4 equal to 7, 5 plus 6 equal to 11, 7 plus 8 equal to 15. Okay, so far so good. I'm just creating aggregations by pulling them together. The putting each pair together, I'm going to do it here. I'm not going to repeat that, but I get these 2, right? Okay, I'm doing it by actually collapsing the 8 nodes graph into 4 nodes graph with the new representations. Now let's see what happened. Okay, it doesn't work, right? Okay, and then why is that? Both of them get 36. Okay, so the sum doesn't work, right? Does the average work? It also doesn't work. Okay. So the hierarchical pooling doesn't work, but why is that?
Does this have anything to do with surjective relationships and the fact that you're losing information by collapsing these numbers into a sum?
So here there's a one interesting thing that are actually very important is the following. Okay, why you need to think about it in this set. How come you cannot actually distinguish graph 1 from graph 2 using this operator? Because they're underlying symmetry, okay, in this set of the number. And then by your aggregations approach, preserve that symmetry, okay? You understand what I'm saying? So under that operations of aggregations, I actually still have the same sum and the same average, okay? Now let me do it in the other way, okay? I'm just trying to change the strategy of the aggregations. The graph are actually still identical. Okay, the graph is still identical, but this time I collapse the first 4 nodes, and then I let the last 4 nodes untouched. Okay, so what I'm doing is that in this aggregation strategy, I break the symmetry, right? You see what I mean? Now in the aggregation form, I have 5 nodes, but then the treatment for the first 4 nodes and then the treatment for the last 4 nodes are actually different. Okay, now I actually have this vector. I have this set of number 10, 5, 6, 7, 8 and 50 minus 5 minus 4 minus 3 minus 1. And then you can seeing that all of the different pooling strategy are actually now all working. Okay, you see what I mean? Does that make sense? So Sabina, you look very. am I saying something? Okay, so far so good. Okay, now so this is just to elucidate a little bit, elucidating that. As you can see, the global pooling is also one of the technical difficulty to actually get a good latent space. And that problem actually become even more severe if you actually have a bigger graph, right? Okay, let's say a graph have million nodes. Okay, why is that? Because the compactions, if you preserve the dimensions of the feature vector of the nodes and try to do it on the graph, you actually compress the data a lot. Okay, so no matter what operator you are you use at the end of the day, if you compress a very high dimensional data into a very low dimensional data, you're going to lose informations. Okay, but then the key here is not to prevent the loss, but can you lose the information, but in the same way also preserve the order and make it distinguishable? Because in the latent space, you don't really care about making it identical, because that's not the whole point of creating a latent space. The whole point of creating a latent space is actually to preserve the property and making the distinguishable remain distinguishable, the thing that are further apart remain further apart, so that when you actually apply the decoder or you do downstream thing, you still have a good vector space that you can actually build a model. Okay, so in a sense, you can actually thinking that we as a human do a lot of reparameterizations in elasticity. We find out, okay, maybe I write the elasticity in the invariance of the string tensor. I just need 3 of them. I could collapse the dimension from 6 to 3. But this is actually a handcraft approach. So here we kind of do the same, except that we're doing with the graph. Okay, so in this case, I just need to formulate this into a more mathematical manner. So what I'm actually doing in this particular hierarchical global pooling is to design the rectangular matrix S that actually have these dimensions. This is a matrix, so it's a Euclidean product space. So this is actually a matrix that are of NL and NL plus 1. And the NL plus 1 is just the number of the nodes in that new layer, 1, 2, 3, 4, 5 in this particular case, and this is the original nodes. I actually need to design, for each of the pooling, I need to design an S rectangular operator so that I can assign the attribute into a smaller nodes. And notice that it doesn't necessarily to be simply when we're actually collecting them, we can also use a different operator. Okay, for example, in this level, I can use the max, and then in the next one, I can use the average. You can actually changing that just to make the thing more descriptive. And one thing that is actually a good exercise in some sense to use the autoencoder to check is that if it doesn't work, you will find yourself cannot reconstruct your original image. Or actually your original graph, which is actually kind of the point of lab 3. In the lab 3 submission, how many of you using what kind of pooling do you guys use? Do you guys know? Or you just use the by default so that you don't actually look into the details? So in the original graph, we have a heat conduction problem that are stored in the graph, and that you do the node embedding and you do the graph pooling. You already submit the homework. I'm sure you know what I'm talking about. Or maybe if you don't look at how you're pulling it and try to changing it. After you get the matrix that actually allow you to reduce the dimensions this, and in the graphical sense, you just try to collapse this. Okay, so S is actually just an assignment matrix. Now, in general, what you actually need to do is actually to collapse this matrix in the simplest form into a collapsed feature vector using this matrix to project the ZL, which is actually in a larger space, to the X to the hidden feature L plus 1 that are actually smaller using this S. So this S, because it's a rectangular matrix, it has the ability to compress a big, longer, higher dimensional vector into a lower dimensional vector. So you get a compressed representations. And the same apply to the adjacency matrix. You simply just condense. Okay, any questions at this point? I think that part is pretty easy to understand, right? I was also wondering if you ever heard about graph theory or graph neural network. Have you seen something similar that you were doing in the computational mechanics work? Okay, we actually okay. So the hierarchical, I kind of complete the graph embedding. I'm not saying that I actually give you all the different informations, and I think that, but I hope that I give you a tour of what the taste of the graph neural network is at the. So imagine you go to San Diego zoos, there are 200 different animals. Each animal could be one type of graph neural network. Okay, so we in a very compressed time, because as a tour guide, I need to earn money from you by sending you to shopping instead of San Diego zoos. So I only want to give you the tour for 1 hour, and then I want to use 3 hours to force you to buy stuff, right? Then that 1 hour, I'm sorry, I kind of make a bad analog. I think I have more consigns than tour guide maybe. But here, what we want to do is the following. Okay, if you can only have 1 hour to see the San Diego zoos, maybe I would actually just let you to see the elephant and giraffe and all the animal you want to see, but I ignore all the other exotic animal that could be highly enrich your knowledge. But if you actually go through that, at least you know in Africa there's an elephant, and then hopefully you find out that in South Pole there is no polar bear or whatever, and then that gives you a general idea of what the animals look like. But I was saying that the zoo is enormous. There's no way that we can discover that, and there are new methods that are actually happening in a very quick way. So every year, just look for the new IP and all the graph conference. You can actually find the new revolutions of the graph. And but here I just want to show you the basic thing is the following. No matter what animal it is in the ecosystem, they have some underlying dynamics, and this underlying dynamic rarely change. And the underlying mechanism here is that in the spatial method, no matter what you did, you at least need to have a node embedding and the graph embedding, and that thing is universal. So what people did, the surgery part, is usually how to do a better node embedding and the graph embedding, or how to combine them to do the both. But then the big picture that we require to talk about, the convert the graph into the vector space, or to do the node embedding and the graph embedding, they are actually quite universal. So when you read the paper, keep that in mind. That will actually help you easier to read the paper. And I think that I will end the lecture here. For the student that actually come late, I have one request. I did not send you anything about the schedule. So I think the easiest way to do it right now is to do the sorting problem right now. I can actually, do you think you can form a line, and then I can assign a particular time? And then I want to have a 30-minute consultation for all the students that are actually are planning to submit a letter grade, or if you volunteer to submit a project, even though you're welcome to do so. Nothing forces you to do that. And then I just want to make sure that this is something relevant. And then that's it. Okay, so next time for the rest of the lecture, I won't talk about the graph. I just focus on the metaphor, and then you may find that some of the ideas are repeat, some of them are actually not so much. And hopefully by that, you can kind of understand the big picture, and then apply it some of the techniques in your research. Okay, so thank you. And then I will just talk to each of you here. I will just try to, can the student involved in the course form the line, and then I will just look at the schedule right now. So thank you. Okay, now something similar to that, and that is actually connected to the geometric multigrid method. In the geometric multigrid method, you have a different mesh, and then you can solve the idea of the multigrid method is that you're kind of solving this. I want to, instead of solving a very fine mesh, I want to using the coarse mesh solutions to somehow help me find the fine scale solutions. And in that process, you can go through a recycle, which means that we sequentially go from coarse to fine and fine to coarse, or we can go to W cycle. And we can actually see those assignment matrix here also in the geometric multigrid method. Here is actually just a restrictions operator that do the following. If you look at one nodes, and by the way, in this case, you can view the finite element also as a graph. And I have this. Okay, the simplest case to construct a reconstruction operator is to throw out the nodes that are actually not in the coarse nodes. So in this case, that would be these 4 nodes. Okay, and what I'd actually need to do to build a very simple restriction operator that allow me to coarsen the information is just to put the 0 into the thing that are actually not on the nodes that are not shared in the 2 nodes. So I can actually using this to reduce the dimension to this, and then I can build a communication between the 2 levels. Here or is actually exists not in just in the machine learning but actually also in the computational mechanics. So now you can actually using that graph pooling as a mechanism to build a multigrid geometric multigrid method. If you do so, make me a co-author, and then it could be your CAS project. But I think this is doable. To be honest, the creations of the prolongation operator that map from the coarse to fine, and then the restrictions operator that mapping the restriction operator that actually allow you to map from fine to coarse, and then the prolongation method that are actually mapping it from the coarse to fine, in many cases analog to the autoencoder. The only difference is that the autoencoder, because you add a lot of ingredient to it to make it very nonlinear, is not really projections. Okay, so in most of the case when we do the classical nonlinear, when you actually do the eigenvalue decompositions or orthogonal-based decomposition, you are applying a linear method to actually reducing the dimensions. The only difference is that the embedding is actually nonlinear in general. But I think that that's it. It's a very short lecture.